Alright, so this is going to be 23.7 through 23.8. And on this assignment, we're going to be learning about lenses. We call them thin lenses, and learning about ray tracing. Essentially, what happens is when you look through a lens, light that's passing through that lens is bent or refracted by the material, but also by the curvature of the material. And so we have these different types of lenses right up here. We have a double convex, which is what we're going to mostly talk about in this section. A plano convex, meaning one side's flat. Convex meniscus. We've got a double concave, plano concave, and concave meniscus. There's different shapes for different purposes and affecting the focal length in different ways. You can tell that a lens if the edges on the outer edges are bigger than the center of the lens, and a converging lens is one that's fat in the middle, thin on the edges. And they have different purposes and different goals. But what we want to know is when light passes through them, where does it gather again? Where do we see the objects that come through, that send light through the lens? You know, if you look through a lens, okay, right here you can see this is magnified, this is bigger. Okay, but where is it? Like, how far back is it? Is it real? Is it virtual? We'll talk about those things here in a minute. For instance, when we use a lens, a converging lens, this is an example, you see that there's an F shape cut out of the light. But as it passes through that lens, it gets flipped upside down. Notice it is bigger. You know, it's bigger than the original F, but it is upside down. But also, it's projectable. Because this can be projected onto a surface, we consider it a real image. If you can't project it onto a surface and get a clear, crisp image, then it's not considered real, it's considered virtual. That we see it and we seem to think that it's there, but it doesn't seem to actually appear on the object. So there's a couple of things that we're going to talk about. One, we'll talk about power scale or the power rating for how strong a lens is. And the power, it's measured in diopters, and it's just 1 divided by the focal length. A lot of these are, because the focal length is not likely to be a meter, there'll be numbers bigger than 1 when we measure the diopters. Okay, it tells us how powerful magnification could be. As opposed to measuring focal length, we might use the power. I guess that's something that ophthalmologists and optometrists, doctors will use. But we're going to talk about how we draw a ray diagram. And I've got some models down below that you can look at. But when we look at a ray diagram for a converging lens, okay, the first beam of light will come out. So this is our object. Think of it as a pencil or anything that's going to be viewed, anything you want to see through the lens. So your eye would be back here, right? See how the eye's back here? We're looking through there and we're wondering, what am I seeing? Well, the light from the tip of this arrow, we're just going to follow that beam of light 3 ways. First, it comes parallel to the axis, and then when it hits the center of the lens, it bends and aims towards the focal point. The second one goes through the near focus, and when it hits the lens, it comes out parallel. Now, right now, we know that this is the point at which the light is going to gather. However, if we've made a mistake somewhere, the way to guarantee that we're correct or that we've made a mistake is by drawing a third ray. It's called the central ray, and we draw it straight through the very center of the axis of the lens and the axis that goes through the center. If all 3 of them line up, that means we have exactly where the image occurs. Okay, a real image will occur on the back side of the lens. What I mean by that is we call the place where the object is the front side. Over here on the other side, we'd call that the back side of the lens. It's virtual if it occurs on the same side of the lens. There's also some sign conventions that we should talk about. If you see this, for instance, with a converging lens, you can see the projection of what's behind the lens. It's looking out the window. You can see it's upside down. Again, we can see that's upside down here. Converging lenses are often real images, but they're also often upside down. The other type of lens is a diverging lens. This one's a little bit trickier. It goes to the lens, but then the light must diverge or separate as it goes away. In order to do that, it actually has sort of a reversal of the way that we create those rays. I'll walk you through that here in a second. But because it creates an image right here that's on the same side of the lens, we consider it virtual. The next thing we talk about is magnification. Magnification can be found by taking the height of the image and dividing it by the height of the object. If it's a bigger height, then it's gotten magnified. But if it's smaller, then, well, it's smaller. Now, magnification can also be measured by taking di over do. Okay, we can take magnification a couple of different ways. Now, the thin lens equation, this is the one that we're going to use a lot. You've already used this with the mirrors, that 1 over the distance of the object plus 1 over the distance of the image equals 1 over the focal length. Where we're going to be specific here and making some changes is in some of the sign conventions. Focal length will be positive for converging, negative for diverging. Object distance is positive if it's on the same side. If it's on the, we'll call it the left, is the way we typically draw this. If it's on the same side the light's coming from, okay? This isn't going to matter until we do combinations, okay? When we do combinations, there's a chance that the object distance could be negative. We'll talk about that in that section. The image distance is positive if it's on the opposite side of the lens, if it's on the back side of the lens. If it somehow shows up on the left side of the lens with the original object, we consider that a negative image distance. Magnification, m equals hi over ho, or negative di over do. And so that's pretty much what you need to know to be able to do this work. That being said, I'm just looking real quick before I jump to my ray diagrams. Yeah. So what we're going to do now is we're actually going to jump to the ray diagrams that I've put in. Now, you might have to flip your head to make this work. Let me zoom in a little bit here. All right, I'm going to zoom in a little bit. All right, maybe one more. These are pretty big pieces of paper. You might have to flip your phone or whatever you're watching this on to be able to see it really effectively. But you can see I've got an object right down here. Let's grab our deal here. Object right down here. The first ray of light comes out. I'm going to go parallel, hits the axis, and goes through the near focal point. The next ray goes through the far focal point. It goes through the near focal point on this one, and then comes out parallel to the axis. And the third one goes straight through the diagonal through the center. When they gather in the same place, that gives us an image. If you look at the comparison to the original, this image is upside down. It's pointed downward instead of pointed upward. So this is inverted. It is real in that it's on the back side of the lens, and it is magnified. It is bigger than it was originally. You can see that my focal length was 10 centimeters. That's positive. The object distance was 15 centimeters, and the image distance was 30. If you use the lens equation, 1 over do plus 1 over di equals 1 over f, you'll find that this actually works out really well. All right, let's take a look at our next example, which is what happens when we bring the object inside of the focal distance. Okay, this is where something big is going to happen here, literally, but also maybe figuratively as well. All right, so let's grab, maybe we'll go pink this time. All right, the first ray of light. I'm actually going to change what my first ray of light is. From the object, I'm going to draw the central ray. Now, this light, because I'm inside the focal point, it'll never gather over here. So we actually backtrack that quite a ways. That ray of light is going to go that direction. But from our eye over here, it's actually going to appear to be coming from further behind. This object's actually going to back up a little bit in its image. The next ray is going to go parallel, and it wants to go down towards the focal point. But the way we're going to see that, so we're actually going to see it converging back here. Okay, if we trace it backwards, it should come back up here. And the last one is, because we're inside the focal point, we're going to follow from the focal point across the top of the object, and we've got to come out parallel. Well, that would send us this way. But notice, these rays are never going to intersect. So it turns out they actually intersect backwards. Now, again, from our eye's perspective over here on the right, we're seeing the image get much bigger. It is backing up just a little bit, but it is much bigger. And it is upright. but because it's on the same side as the original object, it is virtual. This is how a magnifying glass works. This is exactly what a magnifying glass is. It is a converging lens where we want to make sure that our object stays inside the focal length. If you were to take a magnifying glass and go way far back, eventually looking at something, it would go upside down. So, and it wouldn't be magnified anymore. So it's really important that we understand that concept of how those work. Now, diverging lens, these are both the same. Very similar problems. We'll start with this one. Yeah, we'll start with this one. The object right here is on the, oh no, sorry, wrong one. I want to start with this one. Here we go. Object is outside of the focal point. This is going to be very much like the lens we just did. The parallel line is going to not go towards the focal point. It's going to seem as if it's coming away from the near focal point, which means we're going to backtrack this, okay, back to the focal point. The next ray is going to aim for that next focal point. It's trying to get over here. It's trying. But as soon as it hits the lens, it's going to deflect and go parallel. Now, if we backtrack that parallel, okay, back this way, we see that intersection is going to happen. And the last one is through the center, right through the center. And that right there shows us where our image is going to occur, right here. Notice it is upright. It's virtual because it's on the same side. And we're going to say that it's reduced. I think I wrote the word minimized, but I meant reduced. My math brain is going, not my physics brain. But that's how we're going to end up. Notice these rays of light, they diverge as they go through the lens. That's why it's called the diverging lens. But it's still, we still see an object, or what we call an image, on the other side of the lens. So it's important we're still able to track that down. Last one. Okay, what happens when we put the object inside of the focal length of one of these? Well, we're still going to have our parallel ray go out, and it's going to aim as if it came from the focal point on this side. So that hasn't changed anything. Going through the center and going for the far focus. I'm shooting for it, but when I hit the lens right there in the middle, I come out parallel. And if you backtrack that right through the middle there, you should see that we have our image right here. Again, upright, virtual, and reduced. Check out the focal lengths and distances that I gave you, and you can put them in the equation to check them out. But really, this assignment is about making a calculation. And so let's take and make one calculation here. Let's say that we have a converging lens, okay, with a focal length of 15 centimeters. And let's say that we're going to put an object, DO, at 25, no, let's go 60 centimeters. We're going to be back pretty far. We're looking at something that's fairly far away with our converging lens, and we want to know the image distance, and we want to know the magnification, okay? Where is it in its image, and where is it in magnification? Now, we could do this by ray diagram. We could actually lay this out, do a ray diagram, and take all the measurements. I'm definitely not going to do that. However, I will kind of make, there's my converging lens, my focal point's at 15, my object is way out here at 60, okay? So we know the ray of light is going to come through like this, come out parallel, go parallel, and then through some focal point over here. It's going to come through like that. So I'm expecting this to definitely be an inverted real image. It's going to be upside down. It might be bigger, might be smaller. We're going to have to look at the actual calculation. But it should be a positive image distance. So our formula is 1 over DO, which is 60, sorry. 60 to the object, plus 1 over DI. Let's pause it here real quick. All right, this is always the hardest part because I don't remember where I was. I just got paused here. But 1 over the DI equals 1 over the focal length. The focal length is a positive 15 because it's it's a converging lens. Now I'm going to do all of these in centimeters. I know we've always said do it in meters, do it in meters. As long as everybody's using the same unit here, we're good to go. So this would be minusing 1 over 60. That would get rid of the 1 over 60. And then this whole thing gets raised to the negative 1. That's how we flip these. You could do the old Welch rule, 1 divided by your answer, but just raising it to the negative 1 works really well. So 1 over 15 minus 1 over 60, and we raise that to the -1, we end up with 20. So DI would be a positive 20 centimeters. So that's the first step. We know it's inverted, lots of things like that, but we can show that through the magnification, which is negative DI over DO. Well, negative DI being 20, divided by DO being 60, tells me that this is going to be upside down. That's what the negative tells me. And 20 divided by 60 is 1/3. So it's going to be 1/3 the size. This is going to be smaller than it was before, and it's upside down. So, you know, if you think about that, man, that's a problem. We might want to magnify that light, that image, into something bigger. So we might end up using a double lens here in the long run. But anyway, this is how you're going to solve the problems: magnification, image distance, stuff like that. Let me know if you have questions, and we'll talk about it when you come in and ask.